I'll begin with a prayer. Heavenly Father, we thank you for this day and weekend is about to start. Help us to use this time wisely and just pray that we glorify you in what we do, Lord. In your name I pray. Amen. All right, so most of these problems were a welcome relief from what could have happened today. Let's see here. 4, 1 minus 2 is the alleged cross product. 4 times 1 is 4, plus 2 is 6, minus 6 is 0. That's good. This times that is 4 rather. 4 plus 0 minus 4 is 0. It's perpendicular to both. You'd have to be fantastically unlucky to get it wrong. So I think we're right. I think we're good. I mean, in principle, you could take any scalar multiple of this vector and it would still be perpendicular to those two, right? But, I mean, it would take a fantastic coincidence or arithmetic to get it wrong, but a scalar multiple of the right answer. This right here, very good. So x hat cross y hat is this cross that, which when we sort through the definition in this rather narrow column I've given you to work on, gives you a 0, 0, 1, which is z hat. On the other hand, problem 3, we worked out that y hat cross z hat is in fact 1, 0, 0, and you, oh, come on, man. All right, half credit. Half credit. This is, of course, x hat, right? I'm just kidding. Full credit. Z hat cross x hat. Z hat cross x hat is this cross that, which you worked out to be 0, 1, 0. Did you hear that?
Yes.
What did he say? I thought he was like shouting Auld Lang Syne, but that seems wrong. Oh, that's more likely. I once had a student swear very loudly in a class. Like just all of a sudden, just out of nowhere. And then walk out of the class. And never came back. It's true. I don't know why. I wasn't going to discipline him or anything. I mean, I was like, okay, you know. All right, so z hat, oh, this marker is sad. I should throw that one out. Z hat cross x hat is y hat. That is, in fact, true. Now, we can remember all three of these relations in terms of a circle, if you like. Very popular, x hat, y hat, z hat. So if you go like this along the circle, you get to the next one. So you follow the circle, x hat cross y hat gives you z hat cross x hat gives you y hat, and what's the other one? X hat cross, I mean, and if you go opposite the circle, you get minuses, right? So like x hat cross z hat is minus y hat, etc. as well. All right. Another way people write this, which is also fine, is you can just put them in a line and just keep writing them. So this will always tell you, like, you know, what's the next one? X hat cross y hat is z hat cross x hat is y hat, and you can do it like that too. There are various ways to do it. This is sometimes, I mean, physicists tend to like this kind of calculation. Here's an example. If we take, say, 1, 2, 0 cross z hat, we can write that as 1 x hat plus 2 y hat cross z hat, right? And so that gives me x hat cross z hat plus 2 y hat cross z hat, which by our circle of cross products of the unit vectors gives me minus y hat plus 2x hat, right? Right. Of course, you can also do these things with IJK. The recommended homework I gave you out of was it? I can't say his name. What's it? Rogowski. Okay, good. He'll have IJK in place of x hat, y hat, z hat, right? So as you're looking at your homework, be aware of that. And I should make you aware of that in case you have to take some standardized exam later that happens to involve multivariate calculus. It's very likely that they would use IJK. It's just kind of the usual thing. I think that x hat, y hat, z hat's a better notation, so I'm going to use it. I don't think it's so much of a mental imposition for you to learn both. It would not be so insulting as to say that's going to be a mental burden to you. If I said that, I think you should probably write me a nasty email or something. I don't know. Okay, so find the normal and a base point for the plane given by that equation. So you identified x naught equals -2, y naught equals 3, z naught equal to 0. So the base point -2, 3, 0, and the normal 3, -7, 10. Great. Very good. So it's easy enough to miss what when I talked about this last class, so it's understandable. I'm just gonna start. Well, basically, we're just using. Work myself into a. This is not an actual whiteboard. So this here is just what she wrote. 1, 1, 1, and then we do plus t times the. Well, what's q minus p? I'll just go straight to it. It's 0, 1, 1, right? I'm living dangerously, no partial credit for me. R minus p, 2, 2, and that's 8. 8 minus 1 is 7, so 2, 2, 7, right? And so we have the parameterization, which you could also call a patch. It's a patch of the plane, is 1 plus 2s, comma 1 plus t plus 2s, comma 1 plus t plus 7s. There you go. That's a parameterization of the plane. That's not the only one. There are many. By the way, parametric equations for the plane, what would they be? X equals to 1 plus 2s, right? Y equals to 1 plus t plus 2s. I didn't ask this, but just while we're at it, z equals to 1 plus t plus 7s. These would be the parametric equations for that plane. Plane parameterized by that guy. Oh, I may have been holding my laser pointer too tightly. If I shined you in the eye, my apology. I just realized it's bad to hold a laser pointer like this, you know. Any questions? All right. So I thought today, after I got done looking at these problems, I should just take a second to talk to you about physics. So cross product, dot product, what do they have to do with physics? Do they have anything to do with physics? What use are they in physics? Now, some of you probably having heard me utter these words are like, let's just not. But you should get a better attitude. Physics is important. It's not that hard. The part we do in here anyway. So in particular, work, right? Work is force times distance, right? Well, that's the sort of elementary, most basic version of that you see. But if you want to talk about a little bit better, if we talk about a constant force, we should use a vector to describe it over displacement delta r. So that'd be something like r2 minus r1. It's the difference, the displacement vector, your initial position, your final position minus your initial position is your displacement, right? So the displacement vector dotted with the force, if it's a constant force, that gives you the work done. Work done by F over this displacement delta r is equal to F dot delta r. So there you go. That's one of the fundamental applications of the dot product for a constant force, you can take the displacement of the force with the displacement that gives you the work done. Okay? That's an important application. For the cross product, we can talk about torque. Torque. What's torque? Torque is defined to be tau. It's the radial arm cross the force applied. So the usual picture you see something like this. Here's my radial arm. Here's my pivot. Right? If the force is applied like this, usually we don't think of the force in the pivot arm being based at the same base point, right? We're actually taking this is where one of the places, you know, I claim in physics where I was moving vectors around. Here's one of the examples I mean of that. When we take the cross product of the force and the pivot arm, well, the pivot arm is based at the pivot point. But the force, where are you applying it? Are you applying the force at the pivot point? No, unless you're an idiot, right? So, I mean, or you're just trying to trick somebody, like, look, I'm trying to open the door. Oh! You know? It's like, anyway, sorry. You could be an illusionist, right? Oh, sorry, it's kind of a sore topic today. Okay, so getting back to it. And you can see that this is kind of a good formula, right? Because as we discussed, the cross product is largest when the vectors are perpendicular, right? So if you want to open a door, what do you want to do? Do you want to push on it like along, like tangent to the door? You know, when you open a door, you open it up a little bit and then you just push on it towards the hinge as hard as you can? No. You push perpendicular to the door. That's what creates torque, right? And so the torque is largest when the radial arm and the force are perpendicular. This is the right formula to express that. So torque is a cross product. Another thing, a little bit later, physics 232 application, the Lorentz force is Q, the velocity across the magnetic field. So this is the force. This is the force on Q due to magnetic field. B. Q is a charge. V is the velocity of the charge. All right. Whatever that means. You guys know what it means. But we'll learn more deeply as we go on in here. So you can ask the question, if you take magnetic force and you let it act on some particle over a displacement, do you do any work? Suppose that you're in such a way that the force is constant for our current discussion. Don't ask me how that's possible. But it's not going to be possible. I mean, if you just think about a little infinitesimal displacement, think about that then. How about that? If I go from this point to this point, they're really close together, right? So if they're close enough, then this force is, and the particles change. Essentially, the force is constant, right, if we go over a short enough distance, to a good approximation anyway. And anyway, if you look at delta R, right, if we look at the magnetic force, dot delta R, what's it going to be? What will the velocity be, essentially, over a very short increment of time? It's, to a good approximation, the average velocity, right? So this force, right, can I see it yet? Oh, I'm making this too complicated. Let me explain it a slightly different way. So you got a particle, right? It's moving from this point to this point over here, right? The displacement looks something like this, right? What does the velocity look like as the particle moves from there to there? It's also like this, right? The velocity is tangent to the motion, essentially by definition. And so, what about the force? Well, the force is perpendicular to the velocity, right? So what's the work done by the magnetic field? It's 0 because this delta R is in the same direction as V, right? So that means that the force is perpendicular to the displacement for magnetic force. So magnetic forces can't do work. but they can change direction. So there's that. All right. Back to the math. So you guys have any questions about anything in particular? My next thing on my docket is to just start talking more about how the cross product works and trying to look at some of its deeper properties. There are identities which connect the dot and the cross product. They're kind of subtle. No one has a particular hang-up in a homework or something? I mean,
the presentations that you gave us, for some of the questions, it just has the answer to the question and not the question itself. Do you know where we could go to get the questions? Because it's the written out explanations of questions, and in some of them you state the question, but in others it's like...
are you talking about the handout from Rakowski?
No, in the announcement you gave us a couple.
Oh, the problems are stated at the end of the chapter. They're like
in your notes?
in my notes.
Oh, never mind.
Yeah, see, they're like page 83 to 85 or something like that.
Okay,
That's where the problems are. Yeah. Uh huh. Probably not. Problem 3. What is that problem? Huh. Not sure I have much to say about that. I mean, if you have, I guess I can give a hint. All right. So if I have, vectors, right, A and say V, then if I want the part of V which is parallel to A is what? The part of V which is perpendicular to A is what?
Which is project worth, right?
Right, yeah, so we can take A, we can break it up into this, we can take V rather, and we can, stink, picture. I have set myself up for the, so if I'm looking at this, this vector V, and this is my A, say, then of course, yes, I can break V into two pieces. I can break it into the piece which is parallel to A, which, as you just said, is the projection onto A of V. And I can get this piece over here, which is the orthogonal piece. So that's a way I can take P and V and rip it apart into two pieces, which are...
I don't know why that seems difficult. I guess it was the way it was worded. I get what you're saying.
Yeah, that might also involve the cross product. I mean, another thing is, if I want, it depends on the question. I mean, if I want to produce a vector which is perpendicular to a given vector or given pair of vectors, often the cross product is it's a nice way to go. All right. So I think I stated the somewhat unexciting the useful properties of the cross product, distributivity and all that. These ones right here, these are a little bit more difficult. So in particular, if you have vectors A, B, and C in R3, all right, then we have the following relations. We have that A cross B cross C doesn't make sense. without parentheses. So if you put in parentheses like this, you get A dot C times B minus A dot B. If you're ever reading a book in engineering or physics or something and they don't have parentheses for a triple cross product, they don't know what they're doing. Because it's not the same. Like if you take A cross B then cross C, that's different than if you take A crossed with the cross product of B and C. The order in which you do it matters. It's not an associative product, in fact. So this is one of the identities which is known. There's also something called the Jacobi identity, which is that A cross B cross C, and then you do plus B cross C cross A. I'll add parentheses here in a second. And then plus C cross A cross B. Vector, 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 vectors all around. Parentheses on the second too, each time. This, oh, I really, really want to write on the wall right now. I mean, you can use a 0 a lot of times, right? No? There we go. Stay in there. You will stay in there. Ha! There we go. I fixed it. 3, you actually can use this. This is the so-called Jacobi identity. I don't think I've ever found myself really needing to use that. If you find yourself needing to use that in a homework problem, you found a difficult problem, I think. I don't know. I don't know if I've ever used that actually. This one I have used. This is of fundamental geometric importance. A cross B cross C equals to B dot C cross A. These are all what are called triple products. The triple product involves a combination of the dot and the cross product. It gives you a number corresponding to 3 vectors. What do you think that number means? By the way, A dot B cross C, you can also show that's the determinant of the A, the B, and the C just shoved together in a 3 by 3 matrix. If you know what determinant means, great. If you don't, no harm, no foul. Okay? Although I do have the formulas in my notes if you're curious. What do you think it means? Let's see here. What would happen if if any two of the vectors, if any two of A, B, and C lied in the were collinear, if they pointed in the same direction, for example? What would happen to the triple product? Suppose A and B are in the same direction. What happens? The right-hand rule, kind of hard to imagine. You cross your right hand into your right hand, but that doesn't. The right-hand rule breaks down, by the way, in that case. Here, what's a scalar multiple of a vector? A times C is a scalar multiple. What happens when we take CA crossed with A? We get C times A cross A. What's A cross A? 0. So what happens if any two of those vectors, A, B, and C, are along the same line? The triple product is 0, right? What if no two of them are along the same line? Well, it actually follows then that the triple product is non-zero. The significance of the triple product, well, let's look at it geometrically. So here we go. Here's my B. I'll pick on the B cross C one, yeah? So here's B and C, right? My picture's gonna get kind of a mess, but I described last time that in fact, this area here is what? The magnitude of B cross C, right? I haven't derived that yet, I will, okay? But just since we're talking about this triple product, just let me put the cart before the horse just a bit here. Now if A is not, if A is not coplanar actually, we need A to be not in the same plane as B and C. So if A looks something like this, right? If that's A, then you can imagine, making what's called a parallel piped like that. And so it turns out that the meaning of this triple product is it gives you the volume of this parallel piped up to a sign. All right. When would it be that the triple product is positive? As I have it pictured, if you think about B, right? B crossed into C goes what direction? It goes up, right? So if A, B, and C are as in my picture, then this triple product right here would actually give you the honest-to-goodness volume of the parallel piped, right? However, if you were given an A which wasn't like in the picture, if it was in fact down here, then that would work out to minus the volume. So the sign of the triple product has to do with whether or not A, B, and C are what are called a right-handed triple. A right-handed triple is one for which if you take the first two vectors, like so, B, C, A is right-handed triple. What does it mean for BCA to be right-handed triple? It means that if you look at the plane, all right, in which you've got B and C, right, and you calculate B cross C, then A, so if B cross C would be something like this, all right? B cross C, this is B cross C. Now A does not have to, in principle, A doesn't have to be equal to B cross C, but as long as it's on the same side of the plane as B cross C, it's a right-handed triple. So like, you could have something like A is like that. I would still say it's right-handed. It's a right-handed triple if the triple product is positive. It's a left-handed triple if the triple product is negative. That just means that the vector A is on the opposite side of B cross C of that plane. For example, x hat, y hat, z hat is a right-handed triple. You want a right-handed triple for your usual coordinate systems. That's what we're familiar with. Okay, the number 4 is actually what I need to prove the formula here, which I haven't written, which was BC sine theta, where that theta was this angle down here, right? So this is actually equal to, this is what's called Lagrange's identity. Magnitude of A squared, magnitude of B squared, which we could have just written as A squared, B squared in our current vernacular. Sorry about that. Minus brackets A dot B. Or I could just put parentheses, I don't need bracket, whatever. Whatever kind of parentheses you want, it doesn't matter. But the point is, it's the magnitude of A cross B squared is actually the magnitude of A squared times the magnitude of B squared minus the dot product of A and B squared. All right. Oh, poor planning on my part. I cannot put the screen down here. What's that? I do have a smartphone. You got me. You caught me. My flip phone, it's trouble connecting to the cell towers around here. I have to get a smartphone. Look at it. It's hideous. So big and not bendy. I tried it. Don't. but it will take 13 megapixel pictures of my children, so that's good. Okay, so I'll put it over here so I can put that on the projector in just a second here. But A cross B, let's look at this. A cross B squared that's really A squared, B squared, right, in our current notation, minus A dot B squared. What did we say A dot B squared was? We had another identity. I told you A dot B was AB cosine theta, right? So this is A squared, B squared minus AB cosine theta squared. And I think once you write that down, it's really not surprising that we've got A squared, B squared, 1 minus cosine squared theta, which of course is A squared, B squared times sine squared theta, which of course gives me that the magnitude of the cross product is AB sine theta. So if you go through the work to prove that, A dot B is AB cosine theta, and you can prove Lagrange's identity, then you get the parallelogram formula for the cross product. It's not a trivial thing. It's not at all obvious, guys, why the magnitude of the cross product should be AB sine theta if you just, like this versus the definition I wrote last time, the, what was it, A2, B3 minus A3, B2, A3, B1 minus A1, B3, A1, B2 minus A2, B1. That definition, the definition, there is a wide gulf between that formula and the geometric formula AB sine theta. What bridges the gap is Lagrange's theorem, this number 4. Let me show you the proof of it for just a minute, and then I'll put away my toys. Ah! It's so slippery too. Slippery. But then it makes that makes it bigger still. But yeah, I knew I needed to get a case for it. I foolishly put many games on it that my children will enjoy. Yeah. I guess I could look at the page number, but that feels like cheating. All right, so go away. I'm trying hard not to use this projector that much this semester because, I sometimes get in the habit of projecting and just talking from slides, but it's just lazy. And it's better if I write things out, yeah?
So over there, that's the magnitude of the cross product of A and B. You're saying that the magnitude is the same as A cross product of B without those signs?
What? I'm saying the magnitude of the cross product is AB sine theta. The cross product itself is a vector, so...
I was just a little confused.
What I'm saying is it's not at all obvious why this should be true given this formula. Just like it's not at all obvious why A dot B should be AB cosine theta, given that the formula for the dot product is A1, B1 plus A2, B2 plus A3, B3. There's a theorem that says that it's equal to also AB cosine theta. That theorem is non-obvious. It's the law of cosines, in fact. But this identity here is the dark heart of the parallelogram identity for the cross product. Let me show you what's behind the curtain there. So first of all, I should tell you there is a super slick, nice formula for the cross product. in terms of this thing called the Levi-Civita symbol. So this epsilon ijk, it's a sneaky thing. It's 1 if ijk is either 1, 2, 3, 2, 3, 1, or 3, 1, 2. The epsilon symbol is -1 if it's 3, 2, 1, 2, 1, 3, or 1, 3, 2. So in other words, it puts the pluses where the pluses are supposed to be in that formula, and it puts the minuses where the minuses are supposed to be in the cross product formula. So this is just a compact formula for the cross product. You take the ith component of b times the jth component of c times this epsilon ijk. It gives you all 6 terms in one nice sneaky formula. And so if you want to calculate the dot product of A with B cross C, you can do it like this. Though there's also a formula for the dot product, which is just like the sneaky formula for the dot product is less exciting. A dot B is the sum over K of AK BK. There you go. That's a formula for the dot product. But I'm combining that idea. So here, sum over K. This is K. This is the kth component of B cross C. So this is the dot product of that and that because it's this the kth component. That's the kth component of the cross product. So this is the dot product of that and that. And then you combine the sums and move the numbers around. And let's see what else I do. I switch the I 2 spots over. That's a property of the epsilon symbol. It doesn't change the sign. And then again. So that's actually what we're looking at right now as a proof of the cyclicity of the triple product. It comes from the corresponding cyclicity, I can't say this word today, the corresponding property of the epsilon symbol. Now here is the Lagrange identity. Now that we got our feet wet. If you take the sum of an epsilon times an epsilon, you get a difference of these so-called Kronecker deltas. These are 1 if I is equal to L and 0 otherwise. So this is an interesting identity that connects the epsilon symbols. There is, in fact, a tower of such identities if you look at extended epsilon symbols. These are known to theoretical physicists. If you go to graduate school in engineering, you might need to know about them. Anyway, so the length of A cross B squared is that, which is just the product of this and that. I get a pair of epsilons. That pair of epsilons produces the deltas. The deltas distribute to give me 2 sums. Those 2 sums produce the magnitude of A squared times the magnitude of B squared, and the dot product of A and B squared. That's the Lagrange identity. I have seen this as a homework problem in calculus books. Not with this notation, just like work it out, brute force. There's some of you here who could do it, but you shouldn't do it. So anyway, I am just mentioning this wonderful notation, this epsilon and delta notation, because it's an example of what's called tensor calculus, which is sort of a more abstract way to understand vector analysis. If you don't understand it, it's fine. It's not something I tend to test on in here. I might have given you a bonus problem. I don't know. But. All right. So again, all right, I should stop. I have to put this away. I should try not to be lazy. There's one thing I want to show you, though. Let's see, where was it? This is a better picture for the triple product, obviously. So here's my A, here's my B. The area of the base, right, is A1. So that's, A, B sine theta, right? And then, okay, so A cross B would be this n hat direction, right? Like just, that's this direction, the n hat direction, the A cross B. And C doesn't have to be in that same direction, right? So the height depends on, that's the height I'm looking for. The beta is the angle between C and the, well, beta is not the angle between C and A cross B, is it? It's actually a different angle. It's the complementary angle. The angle between C and A cross B, I think, is in here, or maybe it's supplementary to that. I don't know. Anyway, my picture, I called this thing beta, and you can see that this beta, if you look at this triangle here, that's the thing we're after, which is the height. That should be C dot n hat, where n hat's the direction which is perpendicular to A and B. And So that gives me the height. So the height is c. Well, the magnitude of that should give me the height. I mean, my picture assumes a certain orientation for things. If the vectors are oriented oppositely, that could be a minus what I want it to be. So I have to put absolute value over here to get the height of the parallel pipette. And so I get the area of the base times the height. That gives me the volume. And so that's why we have this triple product formula. So I'm sometimes more or less successful in communicating the geometry of this, but that's my attempt. Anyway, takeaway message from this: if you want to find the volume that's given by the three parallel, if you have a parallel pipette, which is just a fancy thing for saying a three-dimensional parallelogram, right? Sort of. It has parallel sides. Each side's parallel, right? This parallel pipette. That's described by three vectors that are not coplanar, right? And the cross product of two, dot product with the third, will give you the volume of that up to a sign. So. The other thing I wanted to talk to you about while I have this out here, since I have it out, would be I've talked about projections onto a vector, right? But you could go a next step. You could talk about projections onto a plane if you wanted to, right? Like if I had, but the thing I would warn you about here is it's important for these formulas that the u hat, the u1 and the u2 hat be perpendicular. If they weren't, then my formulas actually break down. But anyway, just for your information, and maybe I'll work out a numerical example of this in some future lecture. I wanted to just show you this picture. If I have this vector w off the plane, and so I have like u1 and u2 are vectors tangent to the plane, I can take w, I can find the projection of w into the u1 direction. I can find the piece of w which goes in the u2 direction, right? That will give me the shadow of w onto the plane, and whatever's left is the part which is perpendicular to the plane. So we can also talk about projections of a vector onto a plane if I've got a pair of orthonormal vectors on the plane. Orthonormal meaning perpendicular in length 1. So that's kind of neat. I mean, you might find a project somewhere where you actually need to do this kind of visualization. And you don't usually find this in calculus books, which I think we should go a little bit further in geometric visualization and using vectors and projections and things. I think it'd be useful to you guys, but we're too busy doing things like finding maximums of weird trigonometric functions and stuff. So, oh well. Oh, our time's up. Let the weekend begin.